Yeah, I was asked to tell you the solutions of two problems from the home assignment about with vectors. So let me remind you first that we define the ghost component of with vector in such way d. So if n is a power of prime number, when we see that it is equal to such sum. Okay, and we in this home assignment we proved that if we define the sum of two vectors as the sum of the corresponding vector of the sum of ghost components, then this when the sum will be a polynomial from x1 etc xn I1 y1 y and the same for the product. Okay, and so the problem 3b is to show that the algebra of with vector solver if p is isomorphic to p-adic numbers. This means that we consider only such sequences x0, xp, x square, etc. Okay, and this isomorphism is given by we send this vector to a0 to p0 plus 1 1 etc. Here these are Teichmüller representatives, yes, such that they are equal modulo p to this one. So let us show that this indeed is an isomorphism. So let the image of y be v0, v0, p1, etc. And we want to show that, for example, the sum of this one corresponds to the sum of these two numbers, p-adic numbers. Let C be the sum. C is A plus B in p-adic, so C is C0 plus 1, etc. And we can write such equations. C0 is equal to A0 plus B0 modulo P. So C0 plus C1 P is equal to A0 plus A1 P plus B0 plus B1 P modulo P square, etc. And note that here we can take the P power because these are Teichmüller representatives, and so on. So when I will write last one. And the same for A and B. And note that these equations actually are equations on CI mod P. So for this it's clear. For example, for this one, if we change C0 to C0 plus Tp, then the p power modulo p square will not depends on t. And for other equations, it is true too. So this is the system of equations on Ci mod p. And from this definition, we see that we will have the same equations for corresponding x pi. So it will be exactly the same, and these definitions coincide. And for multiplications, the same holds. So we just write here multiply, and for with vectors, it will be the same equations. Okay. Do you have questions about this problem? Okay, so and also problem for A. Here we define f. It sends x p to power 0, power 1, etc. To these powers. So it's Frobenius automorphism, and V it will be right shift. It sends x to 0, and we want to prove that Vf is Fv is a multiplication by p in with algebra. So obviously they commute, and x0 x I mean xp to power 0, etc. Is sent to 0 to p, etc. Okay, and so we want to prove that it is equal to p. P, the Gauss component of p, obviously, the Gauss component of 1 is the sequence of ones, 1, 1, 1, etc. So the Gauss component of this vector is such. Okay, and so we have such system of equation. If z is the result of multiplying x by p, then the p0 is p is equal to p. So here I write the product of corresponding Gauss components, etc. So we want to derive from this system that it is exactly such that z p0 is 0. It is obvious from this equation. Zp1, so here this is 0, and we can cancel p. So zp1 is equal to x0 to the power p. Okay, and after that we can go by induction. Let if this statement is true for k less than n, so z p k is equal to x p k minus 1 p. We want to prove that it is true for p to the power n. Okay, so this is the nth equation. this is equal to this is p times x p to power n ghost component is equal to okay, so this is equal to z z is p multiplied by x, and we want to prove that z is actually this one. Okay, and here it is n. This is for k is equal to when k is equal to n, and after that let us change variable now t. Oh, okay, I'm right first. Here actually t is k minus 1. Okay, and we see that this cancels, and p to the power n z p to n is equal to okay, and from this we get that so this is 0, and we proved the induction step. Why p is such has such ghost component? One has such ghost component because one it's an element which is such that if we multiply x by 1 we get x, and if we multiply every ghost component by this one, sorry, could you in with algebra this ghost component corresponds to the element which so we want that if we multiply every ghost component by this element, it does not change. So this is element yes, these are ghost coordinates. Yes, and here these are equations for this is the system for ghost coordinates. So this is ghost coordinate multiplied. Okay, thank you.
So you construct zero characteristic p-adic integers from finite characteristic field. Yeah, that's wonder, the miracle. Okay, and as for us, today we start the study of Newton polygons. So initially it was this is concept introduced by Newton himself, Isaac Newton, and it was used for solution of say polynomial equations in two variables. If we have like p of x, y equals 0, then we can try to solve at least locally for x, well, say for y as a function of x. It's an implicit function. And this function will be sort of Puiseux series. And it's possible to find its coefficients algorithmically, well, recursively, and we'll do this later on. But Newton polygons, well, somehow is an algorithm recipe to do this. We'll start from some general nonsense, but maybe in a week or two we'll solve just this problem. Okay, so given a polynomial, so now maybe we'll forget about this. In just one variable, so f of x is sum of powers like this. It's a Newton polygon. Is defined as the convex hull, so to say, from below. Of the points in the plane, just 0, 0 starts at the origin, then 1 and order p-adic order of A1, then 2 and p-adic order of A2, and so on, and finally n p-adic order of AN, like this. So, well, for example, let's consider Q3 and the polynomial 1 plus x squared plus 1/3 x cubed plus 3x to the 4th. Okay, so it lies here. And let's draw its Newton polygon. So we start from 0, 0. Then we take the first coefficient. There's no such thing at all, right? Then we take the second coefficient, and its order is what? 3-adic order is. Pardon me? I can hear you, sorry. No, the second coefficient. 0, right. So we take this point. Now we take the third. Yes. Oh, sorry, from 0. Yeah, sorry. Yes. Yes. Okay, maybe, okay, let me write like this, from 1 plus this, to be on the safe side. Okay, so the next point is 3, and as Vey says, the value is -1. The next point is 4, and the p-adic order is what? No, so yeah, here it was for 3 it was 1, 2, 3, 4. So for 3 it was -1, and here's just 1, right? So it's here. Okay, and so we take the convex hull from below, so we get this, and that. Okay, and though, well, there is nothing here, and this point does not count because it's above the this broken line. Okay, so what we get? Well, there's no colored chalk, so we just get this. Fine. So, yes. Well, AI will be elements in the Tate field. Absolutely. Well, we can have fractional, yes, coordinates. Okay. So, there is some terminology. The vertices these are the points where the edges change their slope. Now, slopes well, between the neighboring vertices, they are just the ratios. Well, if the vertices are I, mi, and I prime, m prime, I prime, so the slope will be m prime I prime minus m I over I prime minus I. Okay, and finally, the length of an edge from I mi to I prime to m I prime is defined as I prime minus I, or maybe the absolute value of this. Okay, so this is some standard terminology. And now our first lemma for today is about the slopes. So assume that the slopes are lambda 1 less than or equal to lambda 2, lambda n, and assume that lambda 1 is the same as lambda 2 is the same as lambda r, but then the next one is strictly bigger, and the slopes grow. Yeah, from this picture it's clear. and f of x is 1 minus x over alpha 1, and so on, 1 minus x over alpha n. And these roots are some p-adic, well, Tate p-adic numbers, and lambda i's are defined as the order of 1 over alpha I. Then if there is an edge of slope lambda and length L, then there are exactly L many roots, alpha i's, whatever, of order lambda. Okay. Okay, so sorry, so this was not a formulation of lemma, it was rather the beginning of proof, sorry. So in other words, from the slopes of the Newton polygon, we can find out the orders of the roots. It's an algebraically closed Tate field, so there are many roots, as many as the degree, and their orders can be found from the slopes of the Newton polygon. Okay, so now we take all our slopes and we order them, no, just in the natural order, increasing, and we assume that some well, maybe it's, I don't know, the terminology is not maybe very good. So I assume, in this I assume that, well, here I have lambda 1, also here I have lambda 2, and here I have lambda 3. And in this sense, they are all equal, but then I have lambda 4 that is only bigger than lambda 3. Yeah? Okay. So first check that the first edge is from 0 to r times r lambda 1. So how do we do this? We know that the coefficients AI is, well, plus minus the elementary symmetric polynomials of the inverse roots, well, of the roots, and these are the inverse roots. Okay, so elementary symmetric polynomials. Okay, so any summoned in this elementary symmetric polynomial has the order at least I times lambda 1, right? Because they are all ordered, and you just take the products of I elements here, okay? And hence, by the triangle inequality, the order of the coefficient AI is at least I times lambda 1. And hence, it implies that any vertex of the Newton polygon lies not lower than this line, or the ray, so to say, from 0, from the origin to this line, to this point. This. And it's good, but we have to see a vertex on this ray and exactly at the point R. Yes? 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 Yes, and so what? We ordered all the roots, yeah, and the corresponding lambdas in this increasing order, yeah, and it starts from R tuple of the same orders lambda, and all the rest are only bigger. So whenever we take the products, here, just because we have to take I many of those and sum up their orders. But the minimal possible way to do this is take those i's from the beginning, yeah, because they're ordered this way. And here we get this. So, well, typically it will be even bigger, but at least this. Well, this I is the same as here. It does not depend on R, but R many, yes, and so what? And then bigger, yeah. So when we multiply any I of those, we get at least the ith power of the first one. Huh? Any I. Yeah, yeah. Yeah.
A lot of, we know how many vectors which have this lambdas. This lambda 1 is an order. So we sum up all these lambdas in a number
Yeah.
we have.
Also, you can continue in Russian. There's no point. Yeah. For example, if it's E1, then it's just the sum of all those guys. Okay. Just each of them has order at least lambda 1 by triangle inequality. Okay. Okay. Now we know that for AR, yeah, there is a unique summand of order r times lambda 1, and all the others have bigger order. Hence, by triangle inequality, the order of AR is exactly R lambda 1. Okay? Okay, now let I be bigger than R. Then all the summands have order strictly bigger than I lambda 1, and hence the order of AI will be strictly bigger than I lambda 1, and hence the first edge is exactly as we wanted from the origin to R times lambda 1. Just this. Exactly this. And then after that, we have some bigger slope. So it's the origin, that is R lambda 1. Fine. And then so if at some point lambda s is smaller than lambda s plus 1, but equal to lambda s plus 2, and so on, and equal lambda s plus r, but smaller than lambda s plus r plus 1, then for the same reason, we'll have an edge going from S lambda 1 plus so on plus lambda S to S plus R lambda 1 plus so on plus lambda S plus R times lambda S plus 1. Okay. And so on. And this will be a proof. So you see that it is a useful concept, this Newton polygon, just looking at some very straightforward geometric observables, we observe the p-adic valuations of all the roots. And now we extend this notion to the series. So now f of x is 1 plus the sum to infinity. And would just do the same thing. Well, lower convex hull of, pardon me? Yes. Yes. But that's what we proved, that if well, somehow we do it the other way around. We assume that there are exactly L many roots of order, say, lambda 1, and then we prove that this is the length of the first edge of this slope. But it's reversible, sort of thing. Okay, so we consider this infinite series. Then we take the same points, I p order of the corresponding coefficient, and there we are. But now certainly it can be infinite. We start from here, then we go somewhere else, and this. So it can be infinite. Also, it can end up with an infinite ray. Can have infinitely many edges. Can end up with an infinite edge. Yeah, from the very beginning, like this. For example, 1 plus the sum a x, like this. Yeah, just the powers of ax will look like that. What else can happen? Well, 1 plus p, the sum of x to the I, so then how it will look like? We'll have this point, and then the points like that. So we will only be able to draw just this x-axis, yeah, and this will be our convex hull from below, right? Just this ray will be our Newton polygon. Okay. So there could be some ugly situations. But then we will prove the next lemma, yeah, that is similar to the previous lemma about roots of polynomials. So this is about the roots of infinite series. So if it happens that the series is convergent, and in the domain of convergence, this function admits a zero, has a root, so to say, then this the order of this root can be evaluated from the Newton polygon. So we have an infinite series. This and let lambda 1 be the first slope. So assume that f of x converges on the closed disk with center at 0 and with radius is lambda 1. Okay, and the line, straight line, s equals lambda 1 t with this slope lambda 1 does contain a point I order of AI. So it's not this pathological example when we have the Newton polygon which actually contains no points. Yeah, so we assume that it does contain such point. Okay, so for example, if the Newton polygon has at least 2 edges, then these conditions are satisfied. Okay, so the claim is that under those circumstances there is a root so f of x is 0 and the order of this x is negative lambda 1. Okay, and in fact it's not only in CP but in the disk of convergence. So as stated here. Okay. Fine. So let's prove this. And the idea of the proof is pretty straightforward. We just approximate our series by its truncation. Fn of x is 1 plus the sum from I equals 1 to n ai x to the power I. Okay, so this converges to f of x. Now, since our Tate field is algebraically closed, each of those polynomials will have some root, and from the Newton polygon of the series we can say something about Newton polygons of those truncations, and then by the previous lemma we'll know something about the roots, but then we only have to arrange those roots in a Cauchy sequence that will converge to the desired root of x. Okay, that's the general idea, very straightforward. Let's carry this out. So just for technical simplification, we first assume that lambda 1 is 0, and then we will reduce to this case. Okay, but then the order of other coefficients first of all is positive, and second it will go to infinity as I goes to infinity. Yeah, otherwise we're in this pathological situation. Yeah, if they're all bounded, then the first edge will be just x-axis, and it will not contain any any actual points. If it's bounded, once again, whatever, if it's still bounded, then the first edge must be just the coordinate x-axis, right? That's it. Where are we? Here. Oops. Okay. Yes. Here. No. This cannot be because we assume that the first slope is 0, and actually the first slope can be what arbitrary. But we will we'll first study this case, and then we'll reduce the arbitrary case to this, just by rescaling. X, dividing by this first coefficient, something like this. Yeah. But we assumed that the Newton polygon has at least 2 edges, or that the first edge does contain this point, and in this pathological case, that does not happen. Okay, so let capital N be the maximal I, such that the p order of AI is 0. That is the length of the first edge of our Newton polygon, and well, we take these truncations. Fn of x is 1 plus the sum from 1 to n, and by the previous lemma, Fn has capital N roots, say x n1, and so on, x n capital N, and the order of all these roots are all 0, yeah? Okay. Maybe for n bigger than capital N. So set say x capital N is x1 capital N. Just choose randomly one of them. So what I'm writing. Not 1, but maybe, I don't know, n1. maybe no, maybe capital N1. Sorry. Yeah, we will start from small n equal capital N, and then take one of those roots at random, just the first one. Yeah, and then for all the bigger small n's, we choose x recursively. Xn plus 1 is the one of all those roots. So xn capital N with the smallest distance from the previous one. I minus xn. Okay. So we have a supply of roots of this order at each step, and among them we choose just the closest one to the previous one. Okay. So the claim is that this is a Cauchy sequence, fundamental sequence. And well, its limit will be the desired x. But first, let's prove that this is really a Cauchy sequence. So Sn is the set of all roots of Fn of the truncated series polynomial. Then what do we know for small n bigger than capital N? The distance from Fn plus first of xn minus Fn of xn is Fn plus 1 of xn, just because this is 0. Yeah. Okay, now this is the product over all the possible roots of n plus first polynomial. 1 minus xn over y. Okay. Now this is the product from I equals 1 to capital N of 1 minus xn over xn plus 1 I. And this is so because the among all the possible roots, there are only as many of order 0, and all the others have a bigger order. Yeah, so that will not contribute. So this since norm 1 minus xn over y equals just 1 if y lies in Sn plus 1, and the order of y is less than 0. Yeah, so the orders can be either 0 or smaller. Okay, so then this will be equal this will be equal to the product from 1 to n of the norms x 1 n plus 1 I minus xn. Just because x has order 0 and we can just multiply by it. Yes. So these are roots. All the roots are of order either 0 or smaller, right? The inverse order is bigger than 0. Yeah. Yeah. So this will be this ratio will be of order of positive order. So this difference will have norm 1. Okay. We'll subtract something integral. Okay. So. So why inverse has positive order? It's a root. Yeah, by our assumption, the inverse roots have positive order. So this ratio will be integral. Okay, so this difference will have order 1. So norm 1. Sorry, order 0. Yeah. Okay. So it is this product, and this is at least the norm of the difference x1 plus 1 minus xn to the power n by our choice of xn plus 1, because it was taken closest to xn. Yeah. Fine. So what we proved, all in all, is that xn plus 1 minus xn norm to the power, yes. Yes. I mean, the norm will be 1. We add something close to 0. It'll be very integral, divisible by p, so to say. And so this norm will be exactly 1 by the triangle inequality. Fine. So we conclude that this is at most the difference fm plus 1 over xn minus fn of xn. Okay. But this is equal to the norm of a n plus 1 xn to the power n plus 1. Yeah, just because those are truncations. And if we subtract one truncation from the other, we get just one power. Okay. And again, because we know the norm of x is just 1, this is the norm of coefficient, a plus 1. But this goes to 0 because of our the power series is convergent. And also, well, not only this, but I already erased this pathological picture. We assumed that the norm of the order of A is unbounded. So this goes to 0. Okay, so there we are. So we got a Cauchy sequence. Okay, so it does converge somewhere. The limit of xn is x. Now we have to check that this x solves our problem. So f of x is the limit of fn of x, and the norm of fn of x is the norm of fn of x minus fn of xn, because this is just 0, it's a root. So this is the norm of x minus xn times the norm of ai, x to the power I minus xn to the power I over x minus xn. Okay, and this is at most the norm of difference, because the norms of coefficients are at most 1. Okay, and the norm of the ratio, x to the power I minus xn to the power I over x minus xn is the norm of x to the power I minus 1 plus x to the power I minus 2 xn plus so on plus xn to the power I minus 1, and this is at most 1, because all of them have order most 1. So we conclude that f of x is the limit of fn of x, and this is 0. Okay, so we proved our theorem, our lemma for lambda 1 equals 0. Okay, now we have to reduce the general case to the particular case just by rescaling. So we just divide our variable x by the first coefficient, and this is our rescaling. So for arbitrary lambda 1, choose some element, say pi, in the Tate field, such that the order of pi is lambda 1. And then we set f of x, or maybe we set x, let's say maybe I don't know, y, sorry, y, or maybe sorry. So then we know, then say g of x is f of x over pi satisfies the conditions of our lemma with lambda 1 equals 0. Okay, and hence we know that there is some root such that g of x naught is 0, and the order p order of x naught is also 0, and we set x is just x naught over pi, and hence the order of x naught is minus lambda 1, and f of x is well, g of x0 equals 0, and we are done. So lemma is proved. Okay, and let's prove one last lemma for today. So again, we have a series. And we have a root. Then we set g of x is f of x over 1 minus x over alpha. And it's okay. I mean, in the informal power series, this is just f of x times the geometric progression x to the I over alpha to the I. So it is some series, and well, maybe its coefficients will be 1 plus the sum bi to the power x to the power I. Okay, and so assume this. Well, but don't even have to assume, because we assumed that it converges at alpha, and so then this series converges in the disk of the radius norm of alpha, and okay, and this is actually what we want to prove. So this series g of x converges in this disk. Okay, and the proof is very short. So we have bi is equal to alpha to the negative I plus a1 alpha 1 minus I plus a2 alpha 2 minus I plus so on plus ai, and hence bi alpha to the power I is just fi of alpha. Okay, and hence the norm of bi alpha to the power I is the norm of fi of alpha, and this tends to 0 since f of alpha is 0, and those fi are just truncations as before. Okay, but now since this norm goes to 0, it implies that g of x converges in the closed disk okay. That's it. And maybe let's stop now. The next time, the whole next time, and maybe even more, we'll be proving the Weierstrass preparational theorem. Do you know this theorem from complex analysis? Anybody else? No? Yeah, good. So it says that any analytic function converging in a disk has only finitely many zeros in this disk, and you can find a polynomial with the same zeros. Then you divide and you obtain that the ratio will be analytic function which is invertible without zeros. Okay, so somehow, in a sense, up to invertible functions, holomorphic functions locally are just like polynomials. So all the ideals are generated just by polynomials. So that's what we'll prove in this p-adic context for Tate field. But the proof will take more than one lecture. Thank you. Спасибо.